Hello, I am Miguel Matos, and today I'm going to present FaultSee, reproducible fault injection in distributed systems. And this has been joint work between Miguel Amaral, Miguel Pardal, and myself from the University of Lisbon in Portugal, and Hugues Mercier from the University of Neuchâtel in Switzerland. Nowadays, we are increasingly reliant on distributed systems that we use over the internet for a variety of purposes. And this has been even more true nowadays with the rise of the COVID pandemic. And as you all have noticed, I'm sure, those services, despite being supported by major companies, they still have outages. And these outages have a big impact in our lives, our work. So these faults are highly undesirable, and they lead to system failures where we cannot access the service that we want to. And part of this stems from the fact that systems are getting increasingly complex, and therefore faults become the norm rather than the exception. So it is very important for us to subject those systems to different faults, to different fault patterns, to understand their behavior and be able to build, therefore, more dependable systems. So, and this is the major motivation behind this work. How can we design a set of tools, a language, a platform, such that we are able to easily subject those systems to well-defined fault patterns, understand their behavior, and design better systems such that those faults do not become service failures. This is our key motivation in this work. However, achieving this is quite challenging because of the complexity of the systems. It's not easy to capture the system configuration, the binaries, what are the settings and the parameters that have been used, the faults that we want to inject, which types of faults, when to inject them, in which components, and all of this is quite difficult to capture in a research paper. And finally, we want these experiments to be reproducible, because otherwise it would be quite difficult to take strong conclusions about the experimental results. Let us consider one hypothetical scenario that we can find in many research papers of an experiment that tries to do the following. In the next experiment, we assess the behavior of system X under Y% packet loss for 150 seconds. But even though the authors are telling us that they are dropping packets for this given percentage or for this given time period, this information is not enough. And the reason for this is, depending on the way we implement the fault, this can lead to very different results. For instance, these authors have shown before that depending on the fault injection techniques that we use, we can get quite a substantial impact on system throughput. And on the left, we have a given technique. On the right, we have some other technique. And even though the system is the same, the throughput is rather different just because the fault injection technique is different. And therefore, two different researchers, if they choose one technique or another, they can reach quite different conclusions. So we need further information. What fault injection technique was used? Which one was more appropriate and which one led to better and worse results? And usually we don't have this kind of information anywhere in a paper. So we need the tools to capture these different aspects of the system, and those tools should help us build better and more reproducible experiments. So the related work is vast, but doing a generalization, most of the work either focus on building artifacts that in a way, such a way that those artifacts are reproducible, but disregarding the environment and the fault patterns that might be subject to, or they focus on evaluating large-scale systems under a particular randomized sequence of faults and assess the behavior of the system. So with FaultSee, we aim to address this problem. First, by designing a language that concisely describes the experiment and captures as much information as possible about the experiment, And second, we want to also have a tool that picks this experiment and is able to automatically and efficiently execute this experiment. So for artifacts, we leverage existing work, and we essentially assume they are described as Docker images. So Docker is already very powerful to describe existing artifacts, the configuration, and so on, but not the environment. So to specify the environment, we have a domain-specific language where we allow to detail things such as the seed used for randomized experiments, the number of replicas, the life cycle of replicas, and so on and so forth. Then we have the notion of events in the system, and these events describe moments in where the state of the system changes. So if we look at this example, we are saying in line 14 that at time 10 seconds, I am going to start a service called Cassandra, and I am going to start one replica as specified in line 18. One thing that's also important is to specify how we inject the load in the system. So we treat the client of the system with the same care as the system under evaluation. For instance, in this snippet, at time 1400 seconds, I want to start 2 instances of the YCSB client. Similarly, this is the way we specify fault injection. So in this snippet, at time 2000, I want to inject a fault on a specific node, node number 1, as we can see on line 47 of the Cassandra service. And what fault is this? This is a kill fault. So rather than killing some nodes at random, which might lead to different results if the system is heterogeneous, I am explicitly saying I want to kill this concrete replica. Of course, sometimes we want randomization because this might be important for the experiment. And the way we control this and the way we make this reproducible is through specifying a particular seed for this experiment. And also here I'm saying I want this to be a kill fault. So precisely this means that I am going to kill the process that is running inside this container. So I'm not killing the operating system. I'm not unplugging the network cable to fake that the process has died. I'm really killing the process with a seed kill. So most of the language elements can be parameterized and allow us to reproduce quite complex experiments. But now, for the sake of brevity, let's focus on the FaultSee platform that picks this language and automatically executes a concrete experiment. So this is the architecture of the FaultSee platform. We assume an infrastructure with a working Docker environment and SSH access. We have support currently on FaultSee for Amazon Web Services, Google Cloud, and a local cluster. The master controller is responsible for picking the FaultSee description language and converting this language to a concrete execution plan. The main objective of this is to avoid coordination or communication between the master controller and the local orchestrators, which run the actual experiment, and among the local orchestrators. So this allows us to have better scalability than having to constantly communicate between all of these instances. The local controllers receive this intermediate representation and start to execute it by starting and stopping instances, injecting faults as described in the experimental plan, and they also gather system and application metrics that can be later analyzed by the experimenter. And finally, we have a web-based dashboard that allows us to see the metrics and logs and other information about the experiment in visual interface and also control the experiment from this interface. So with this quick overview, let's now move to the evaluation. And here, our goal is to assess how good is FaultSee when modeling a real-world fault injection experiment. So for this, we pick an hypothetical experiment with the Apache Cassandra database. So, and if we want to write about this experiment in a systems paper, we would probably write down something like this. We set up an experiment with 4 replicas of Apache Cassandra. We subject the system to load using the YCSB benchmark for 30 minutes, and during the experiment, kill 1 replica. The goal is to assess the impact of the fault in the system throughput. And now our goal is to go over the reasoning that we use to convert this into a real experimental plan. The key information here is that we have 4 replicas, that our benchmark is YCSB. We kill 1 replica. We don't say when, however, and we also say that our main objective is to measure system throughput. So if we put all of this information together, we would have experimental description similar to the one we have here, which in fact is the same that we saw in the snippets before. So in a few dozen lines, we are able to convert an imprecise textual description in something that is very precise and concisely describe an experiment. So we ran this experiment on Google Computing Cloud and one standard one servers. On the y-axis, we see the number of nodes, and on the x-axis, we see the time in seconds. So as we can see, we start each one of the Cassandra replicas over a 600 seconds period. Then the YCSB benchmark is started, and we kill the 1 Cassandra replica at the instant 200 and 1000, and later we add a new node. So this is the visual representation of the life cycle of the instances that we just specified. Here we have our metric of interest, the throughput over time. So in the x-axis, we have the time, and on the y-axis, we have the number of operations per second. And as we can see, the impact of killing a node is non-negligible on system throughputs. And after adding a new node to the system, we get back to the original values. So our goal, again, in this experiment is not to discuss what can be done about Cassandra for prevent this drop. Our goal was to show how easy and concisely it is to express these experiments. Now let's say that we want to devise a new experiment, and rather than killing a process, we want to exhaust the CPU of replicas and see what is the impact of this in the system. So this is very easy to do in FaultSee, and it would simply amount to modifying the part where we specify the fault to, rather than be a kill fault, we would inject instead a CPU exhaustion fault for a given amount of time. And this is the throughput over time when the system is subject to this type of fault. So as we can see, exhausting the CPU also has a significant impact on system throughput, which is kind of expected. So after we have an initial experiment setup, it's rather easy to devise new experiments and play around with a wide range of different scenarios. So in this paper, we advocate for the need to have a very precise and concise language to describe distributed systems experiment. And this includes describing the system, the workload, the environment, and the faults that are injected. So all of these together are very, very important for us to achieve better reproducibility of experiments. We propose a language to specify such experiments and a platform to execute them. And one of our goals was to make the running these experiments as easy and seamless as possible. So if you have your system already under Docker, it should be very easy to try FaultSee and see how it behaves under different fault patterns. The prototype is publicly available at minor.science. So if you are interested, please try it out and give us feedback. We will be glad to have it. And to conclude, so thank you for your attention, and I will be glad to take questions.